Hello, everyone. My name is Nathan Peck. I'm a developer advocate for container services at Amazon Web Services. And today I'm going to be introducing ECS Service Discovery, a new feature that we recently added to the Elastic Container Service lineup. So first of all, let's set the stage for what Service Discovery is and why it's needed. First of all, there's a lot of different applications. They're communicating in different ways. Whether it's an IoT device across the room, making functional calls, to a modern application that is geographically distributed, is making requests across cities or even continents. And it needs to be able to communicate with other versions of itself or other application services using known endpoints and APIs. And in order to solve that problem, Service Discovery aims to give the different services dynamic names, numbers, and locations in order to allow your application service instances to find the endpoints of other applications and connect to them. So Service Discovery is particularly relevant in a microservices environment because there's a couple of problems that arise with microservices. The first problem is from the developer perspective. If I'm building a microservice and I have a variety of services that are part of my environment, how can I build my apps such that they can reach the other services by name without needing to necessarily know where those services are? And then from the operations perspective, if I'm operating a bunch of microservices in my cluster or as part of my environment, how can I ensure that I can provide a name? And how can I ensure that it resolves to the right IP address and port? Make sure there's no conflicts, even if I'm running, for example, Docker containers that have been packed onto my instances. So Service Discovery is the solution to both of those problems from the developer and the operations perspective. So what is Service Discovery? It's basically a way of solving this question of where is Service X? I want to talk to Service X, how do I do so? And it solves that problem by giving you a friendly name which resolves to an IP address and port of where that service is located. So for example, the friendly name could be app, and the address could be one of these two IP addresses and port combinations that you see on this slide. So why is it a non-trivial problem to solve? Well, first of all, modern application architectures are dynamic by design. They're scaling up and down. They have a different number of containers and instances, perhaps, for the various different services. And they're changing throughout the day. They're scaling up and they're scaling down. Many workloads are even running on spot instances. So as a particular workload maybe loses the bid on a particular class of spot instance, that workload needs to be moved to a different machine dynamically. And now those IP addresses and ports for that service have completely changed. Additionally, many organizations are now doing blue-green deployments and automatic upgrades in place of their application. And so they want to be able to roll traffic over to a new version of the application automatically. So in evaluating different solutions for this non-trivial problem, Service Discovery, there are a few different things to consider. The first is the Service Registry itself. So where is the information about the different services being stored? And how much do I have to manage about this storage engine? Is it something I'm going to have to scale if I have a lot of different services or many different requests for the services? How hands-on is the registry itself? Second of all, the registry mechanism. So how do I actually get services into the registry? And once again, the major question here is, how complicated is solving that problem? Is it something that I have to do a lot of setup myself, or is it automatic and magical? And then the discovery mechanism. So if I do want to talk to one of the services that has been registered into my service registry, how do I do so? How complicated is that? So the major current patterns for solving this service registry problem, they all have the common feature of requiring some installation, some setup, and some management. So we're going to look at a few of these different solutions, starting from load balancers and then progressing to key value stores such as etcd, console, and the modern concept of service mesh as well. So first of all, let's look at load balancers. So load balancers are a form of server-side discovery. And there's benefits and drawbacks to this approach, but it has worked very well for a long time and will continue to work well for a long time as well. Basically, with a load balancer service discovery, the different application instances are registered into the load balancer, and load balancer exists as sort of a middle component that sits between your client and the server that your client wants to talk to. And that load balancer serves as the registry. It stores the information about how many different server-side application instances there are and what their addresses are. And then whenever the client needs to talk to one of those, the client actually talks to the load balancer, and then the load balancer takes over from there and forwards that request to a server, gets the response back, and sends it back to the client. So this tends to be pretty easy to install and manage, and it scales well, particularly if you're using a service like application load balancer or network load balancer that is fully managed by AWS. But it has the one downside that there are more hops. And so for some very time-sensitive workloads, you may be unhappy with the addition of extra latency between the client and the server, or the fact that the response and request go through this middle entity. So another approach is the DNS-based client-side discovery approach. So in this system, once again, we have a client and we have multiple different instances of a server that the client wants to talk to. In order for that communication to happen, though, the addresses of these servers need to be registered into a service registry, and then the client can actually fetch information about this list of application instances from the service registry, and then the client itself actually chooses which one to communicate to directly. So rather than the request going through this middle load balancer, which will then route it, instead the client has to understand the format of the service registry itself, and it has to understand how to send traffic to one of the instances from that registry itself. There's a few different tools that you can use to solve this problem. So for example, Console, etcd, and Zookeeper, they all serve as ways for you to register the information about these backend services into a registry, which is the Console, etcd, or Zookeeper portion. And then the client can actually query that registry to get the list of services, choose one of them to communicate to. But it does have some downsides, because what you end up having is you have this very complicated key value system to query. And it requires some custom layers to actually fetch information, choose one of the values from that key value store, and then send traffic. And it doesn't always represent the true state of the service. So perhaps the service has been launched, but it's currently in an unhealthy state. It has been registered into Console or etcd already, but it's unhealthy. So you need a lot more handling on the client side in order to detect situations in which one of the services that's been registered into the registry is actually in an unhealthy state and isn't accepting the traffic that you're trying to send to it. So looking at these different options, we get the sense that maybe there's an easier way to do it. Maybe there's a way we can make this less complicated. So the common things that are nice about the system that currently exist is predictable names for services. So we'd like to have one service be able to talk to a different service and just reference it by name without needing to know anything other than the service's name. It's nice that the registry be automatically updated. So if a particular application instance has gone out of service, we would like it to be automatically removed from the registry as quickly as possible. We ideally would not like to manage anything. So I don't want to have to scale an etcd or Console or Zookeeper as I increase the number of services in my cluster. And I also don't want to have to scale that as I increase the number of requests that my application makes to another backend service. Most importantly, I want to be highly available. I don't want anything to be a choke point where if that part fails, my system goes down. And I want it to be extensible. I want to be able to have multiple different environments. I want to be able to add different types of services on different ports and have the system able to handle all of these different cases that I might predict. So this is why we introduced Managed Service Discovery for ECS. And from both the developer and operations perspective, it solves problems on both sides. So for the developer, you can now build applications where your services can invoke another service by name, and the name resolves to an IP address and port automatically. And then from the operations perspective, as you deploy the service, you can just turn on service discovery, and it automatically creates the service endpoint that dynamically resolves without you needing to install etcd or console or zookeeper or handle any extra resources on your AWS account that you need to manage and scale. This ECS service discovery, it's powered by Route 53, so it has all of the same high availability and reliability that you would expect from Route 53. And the way it works is ECS automatically updates Route 53 records in Route 53 as tasks are registered or deregistered from your cluster, and then Route 53 provides an endpoint which resolves to the address of one of those tasks. So now I want to show a demonstration of what this looks like in action. So first of all, I want to show a demo that has been put together by one of my coworkers, which demonstrates what it would look like if you have multiple different services. So he's put together a diagram here showing how this particular application works. Traffic comes in from the internet. It hits a auto-scaling group that is this front-end web page you're currently seeing. And then behind the scenes, there's any number of different services that have registered themselves as available services to be communicated with. And here you can see on this web page a list of the different services that have been created. And if I refresh this page, what you'll see is different IP addresses pop up for this worker here because there are multiple different backend services behind the scenes. Now I want to show how you can go ahead and create this particular system yourself. And to start out, I'm going to create a new service in the ECS console. I'm going to choose Fargate for this, and I'm going to call my service Service 3 and launch 2 of them. I'm going to choose my default VPC and specify a couple of subnets to distribute the tasks across. I've chosen to give my services a public IP address. I'm actually not going to choose a load balancer because I want to use the new optional service discovery feature. So here you can see it's filled in a few defaults for me based on the state of my account. So it's already chosen a local namespace that I've created earlier. And it's already filled in a default service name for me based on the name that I specified for the ECS service itself. So I'm able to take this information, I scroll down, and I'm going to specify that I want this to be an A record for this particular application endpoint. I click Next Step, and I'm not going to set up auto-scaling at this time. I review the settings that I specified here and create service. Very quickly, I'm able to go in here, and while it's launching tasks for the service, let's look at a service that I created earlier that has auto-scaling and service discovery setup, and that's Service 1. So here you can see under the service discovery section of the service details, there's a service discovery endpoint, service discovery name, and I can see information about the DNS record type that's been created for this service discovery endpoint. Now, how I'll actually use this service discovery endpoint. So if I'm in an environment here, and this right here is a Cloud9 development environment that's running in my AWS account, I can actually reference the service discovery endpoint that I got from that service page. And I can see here that there are 2 responses. If I go back to the ECS service details, there are 2 tasks here, and each of those tasks has its own IP address. And what I'm seeing here when I look up the DNS record for this service, I can see those same 2 IP addresses here on this list. And it's important to mention that this particular command only works in this Cloud9 environment because this is a private service registry endpoint that's only accessible within the VPC. So if I was to make the same command from my host computer, I would not get any response. So the IP addresses of my individual internal services are protected within the VPC. But inside of the VPC, I've set it up so that way my other services are able to hit this endpoint and get the IP addresses of the services they want to talk to. So how might I actually use this? Let's add another command to actually choose one of these IP addresses randomly from the list. So here I can see that it randomly selects one of the IP addresses from that service discovery endpoint. And to make it a little bit more fun, I'm going to go ahead and make a web request to that endpoint and see what the response is. So here I can see I'm able to make a web request, and I see two different application instances and IP addresses that the requests are going to, and I see the response from my application on both of these endpoints. So what I've just implemented here very quickly is service discovery and some very simple client-side load balancing to distribute requests across the two different IP addresses that have been registered into the service registry for this particular application. So moving on from this demo, let's talk about some of the use cases for this particular service. So as you can see, there's a variety of different naming schemes that you can follow for your service registry, which enable different use cases for how your applications are organized and categorized within your cluster. So for my demo, I just had a very simple service1.local and service2.local, but I could add another layer to it and actually say my application.staging.local and my application.prod.local if I have multiple different environments. I can have internal microservices as well as external microservices. So I may provide a public-facing service discovery endpoint for my clients to utilize while providing a internally facing service discovery endpoint for different internal services to communicate with each other. I can have communication across multiple different services. So perhaps I have some services in ECS and some in Kubernetes under EKS. Perhaps I have some on-premise, some in ECS, some on self-hosted on EC2. I can actually expose all of these services to each other and allow them to communicate with each other across these different boundaries using security groups and using service discovery. So what's new that has enabled this to be built? Let's dive deep into some of the features underlying in AWS that allow this service discovery feature to work. The first is the service registry in Route 53. So Route 53 has provided some new APIs to create resources on your account that keep track of services and allow you to auto-name the services on those namespaces. And we added in ECS the ability to tie this feature to your ECS lifecycle. So the ECS scheduler, as it takes your process through scaling into registering a task or deregistering a task, it will update these registries in Route 53 automatically. And it's also tied to task health. So if one of your particular containers starts failing its health check, ECS can automatically unregister it from the Route 53 registry. So the end result is that ECS is going to help you always maintain the latest state of your environment in the service registry dynamically and automatically. And here's what that ends up looking like. Here we have this application in the cluster. You see there's a application that's spanning two availability zones with different IP addresses. And I see on the right-hand side two different service discovery endpoints, web.myapp.local and app.myapp.local, that have the IP addresses of those tasks registered. And once again, here you can see in this slide, I can just use a simple dig command to fetch the IP addresses for the tasks from the registry. Now, the main benefit of this approach is that you only have to set up once and you can use it forever. Rather than having to manage an etcd, worry about is the etcd patched, is the console patched, is Zookeeper patched and up to date. I can take advantage of the fact that Route 53 is always up to date, it's always secure, available, and scalable, and I don't have to manage anything once those records are in Route 53. Additionally, Route 53 is going to provide me with public APIs that I can use not only in AWS, but from outside AWS as well if I need to, using the AWS API authentication. And it works across my AWS services, across my clusters and accounts, and availability zones. Let's talk a little bit about Amazon Route 53 auto naming to understand the capabilities that are there under the hood to utilize. Route 53 auto naming is what powers the ECS service discovery by providing this way to register the service names in and then discover the service details back out using DNS-based querying. So the concepts to understand as part of Route 53 auto naming are namespace. This is where you provide an environment name. So in the demo that I showed earlier, that environment name was just local. But I could provide any number of different classifiers to specify what this namespace is. So I could say this is a test environment and it's internal, or I could have a test.external, or I could have a production.internal, production.external. These are all examples of classifiers I'm able to put together to create a specific namespace that all my services of that class will live within. And then within that namespace, as I mentioned, there are different services. So I could have a front-end service that is in the test.internal namespace. And then the service has a service instance, which is the actual details that point to that particular container or that particular application, which is the IP address and port. So just to sort of diagram how they all fit together, you have the staging internal namespace on the outside. Within that namespace, you have multiple different services. And then within the service, you have multiple different service instances. There's a number of different APIs that you can use to manage the different resources on your service registry. The main ones that you would focus on is, on the highest level, creating a namespace and getting the information from that namespace. This is very useful if you have a CI/CD environment and you want to be able to spin up new complete sets of services in order to run tests against, or for your development workflow to give developers a way to spin up a set of services to communicate with and use locally. And then at the service level is where you specify one of those individual components that's going to run within the namespace, deeply linked to the actual service in ECS. And once again, ECS will handle a lot of this for you automatically. But if you're interested in doing it, you can use the service management APIs as well to fetch a list of services. So this can be useful if, for example, you want to query for the availability of another service in your environment. You're not actually sure whether your environment that's currently running includes another service that you need to utilize. Well, you can use list services or get service to check for the existence of that particular service in that environment, and then respond accordingly. Perhaps if one of the services is unavailable, you could fail gracefully and provide an error message instead of crashing. And then finally, the service instance. This is the piece that actually represents a running application process or container that's part of your system. And once again, there is a set of APIs provided by Route 53 for adding instances and registering them, getting their health status, etc. And ECS will do this automatically out of the box. However, you do have the capability to utilize these APIs and tie into them more deeply if, for example, you wanted to implement your own custom client-side logic for registering new tasks across systems or fetching a list of the instances that are part of your service. This diagram shows the sort of life cycle of a service being registered in ECS and how different pieces get registered into the system, named in Route 53 auto naming, registered as DNS record in Route 53, health checked, and then finally they're made available on the DNS endpoint that's part of Route 53. So let's talk about discovery over DNS. The sort of basic parameters of it. So Route 53 uses multi-value answer routing. And so what that means is you can have any number of different values for the Route 53 record, but the DNS query is only going to return up to 8 healthy endpoints. So if you have a very large set of services, only 8 of them will be provided back via the DNS query at any one time. And then the application has the ability to select one of those 8 in order to send traffic to based on whatever criteria that it chooses. So the auto naming benefits, it is a managed API, so you don't have to scale or manage anything. It's a regional control plane, so it's highly available, and it's available across regions within Amazon, as well as within one region. And we have a 100% availability SLA for Route 53 DNS. So you can really count on this system, rather than having to worry about, well, if my etcd goes down or my console or zookeeper, with Route 53, you don't have to worry about it going down because we are committing to 100% availability for Route 53 DNS service discovery. Under the hood, let's look at some diagrams of how this Route 53 service discovery is operating in the ECS cluster. Here's an example of a small cluster that has 2 services, one that's called blue and one that's called green. And I can see in here that there are 3 different blue service tasks and 1 green service task. And the way they got placed into this cluster was by using the ECS control plane. And so what that allows us to do, if we're using the same lifecycle of the service discovery, optionally enabled as part of the ECS service, is ECS will, as it places something into a EC2 instance in one of your availability zones, it'll communicate with Route 53 to create a namespace for that service. And when it starts a task, it will query the details of that task to see what its particular unique IP address is for that task that's running in one of your cluster instances. Once it has that IP address, it's able to talk to Route 53 and register it. And then Route 53 distributes those ECS task endpoints across the different DNS servers that are specified there. So here we see there's a blue.colors.local and green.colors.local, and they each have their own set of IP addresses that point to individual tasks from your cluster. Now, as I scale up, this continues to be true. So here I've added another blue task to the container, another blue task container to that AZ2 instance. And once again, it gets registered by ECS, and Route 53 takes that updated IP address, that additional IP address, and adds it to the blue.colors.local private DNS endpoint. So in using the system, it's important to consider some of the requirements and limits of ECS service discovery. So the first limit is that any task that's using service discovery must use AWS VPC network mode. So this is kind of an important limitation because AWS VPC network mode does also add a limit to how many tasks can be placed on an instance that are using AWS VPC network mode. There is a limit to the number of Elastic Network interfaces that can be attached to an individual instance. And then that limit would then become also the limit of the number of service discovery tasks that are on that instance. So in considering that, you kind of realize that you may not want to use service discovery for every single task in your cluster. For many of them, you would want to retain the use of a load balancer with bridge networking mode, so that way you can have that load balancer sending traffic to different ports automatically. But for some of the applications that really need very low latency and reliable communication from one client to another, you could choose to optionally enable AWS VPC for that particular type of task and service discovery for that task in order to reduce the latency between one service and the other service. Another requirement and limit is that you have to specify container health check. If you are using AWS VPC mode and you're using service discovery instead of using load balancer, you don't have the load balancer to hit an endpoint on that container and verify that that container is still there, still running. So you need to specify another type of container health check, whether that's a Route 53 health check or whether that is a Docker container health check that was also added recently to the ECS service. And then another requirement limit is that the console workflow, it currently assumes that there's a one-to-one-to-one mapping between VPC, cluster, and application. So what that means is you can't really have an application that spans multiple clusters or multiple VPCs when you're using service discovery. You can have a service that is in multiple VPCs, but they would each have their own service discovery endpoint for that particular VPC. Another limit is that service discovery is dependent on Route 53 propagation. As you register and deregister IP addresses, there is a sort of expiration period on the DNS record. And Route 53 DNS record propagation can sometimes take a little bit longer than, for example, an application load balancer updating. So if you've added a new task, it may not show up instantly on the DNS record. And if you remove a task, it also would not remove instantly from the DNS record. So that means it's important to have on your client side logic which will check that query and retry if, for example, one of the IP addresses that it received was an IP address that had gone out of service and was removed from the Route 53 record, but that Route 53 record change hasn't yet propagated over DNS to your particular machine that's making the request. And the final limit is that when you're using a private VPC, you have to have the container health check only. You can't have a network health check. This means you need to specify a custom Docker health check in order to make sure that that container is up and running, and rather than really counting on a load balancer or some external process to hit that container over the network and verify that it's actually there. So how do I get started using service discovery? Well, we have launched it for both Fargate and EC2 launch types as part of Amazon ECS, and it will very soon be available for Kubernetes within EKS as well. You can see this GitHub link has the source code for the external DNS system that's being built out around service discovery for Kubernetes as well. And we're rolling this feature out across many different new AWS regions. It's going to be available in every single region where Amazon ECS and Route 53 auto naming are both available. And so if you are ever wondering, is it available in this region, you can refer to this link, which has a list of different products that are available in the different regions, and check for the regions that have both ECS and Route 53 auto naming available. So I encourage you, if you would like to learn more about ECS, check out the documentation and resources link here on the slide, or feel free to email me, tweet, or reach out on GitHub at any time, and I'm available to answer questions about ECS, auto scaling, service discovery, and anything else you may wonder about containers.